So do you see my screen?
Yeah.
Okay. So the quotient topology is basically what allows us to turn a cup into a donut or turn a rectangle to a torus or do a lot of transformations, which it allows us to do the transformations which we've probably heard about before hearing anything about topology. At least that's what I got. So our definition for a quotient map is if x and y are topological spaces and P mapping x into y is a surjective map, then P is a quotient map, provided that if a subset U is open in Y, it's open if and only if its inverse image is open in X. So it is stronger than continuity because it has two more conditions. So one of them is that it is a surjective map, and the other is if and only if. So for a continuous map, it's only if, as I have pointed out here. So if U is open, then its inverse image is open. For a quotient map, it's if and only if. It goes both ways. So these are the differences between a continuous map and a quotient map. So there are two equivalent statements to our definition for a quotient map. And the first is that if a subset A is closed in Y, if and only if its inverse image is closed in X. And I missed the part, I think I missed the presentation to point out that P is a surjective map again. So we get the proof by, let me write it down. So, okay. We know that A was its complement equals Y, and then the inverse image of A equals the inverse image of Y minus AC. Which would equal X minus the inverse image of AC. So basically when AC wouldn't be an open set since it's the complement of a closed set. And if we know that this is a closed set, then it follows that this would be an open set. So a complement is open and its inverse image would be open is equivalent to A being closed and its inverse image being closed. And I will leave this here for a little.
Well, a very quick comments on your notation. So usually we don't really use this plus means the union of two sets, because you know in some set or in a lot of situations, a set, the element of a set may have the addition as an operation. Then one set plus another set means any element in the first set plus another element in the second set. Okay, then this would be the addition. So this is slightly different from the subtraction. But usually, well, for the set subtraction, we also don't use this minus sign. We always use the slash sign. But in this textbook, it's fine. This is not very. This is not as confused as plus sign. So for minus sign, it's better. Okay.
Okay. I will write this down for myself so I can keep it in mind for the next time. Okay, so the second part is that we define a subset C to be saturated if it equals the complete inverse image of a subset of Y, or if we have A belonging to Y, we would have A would equal, wait a sec. I'm sorry, A belonging to X, our map is X to Y. Then A belongs to X, then A would equal the inverse image of P of A. So something that got me a little bit confused, so I was on this part, is that actually there are two definitions for saturated sets. So some authors would use saturated for a set which is an intersection of open sets, and some authors would use saturated set for this kind of set. And the two definitions are different. But in our book, in this section, we use it only this way. We don't use it the other way. So if P is continuous and it maps saturated open sets of X to open sets of Y, or it maps saturated closed sets of X to closed sets of Y, then we can, that statement is equivalent to saying that P is a quotient map. So let us prove it first. If we assume that P is a quotient map, and we have to prove that it would be continuous and it would map saturated open sets to open sets of saturated open sets of X to open sets of Y. The proof is pretty much the same for closed and closed sets. So the proof which we're going to use for open sets is going to work the same way if we change everywhere where we use open with closed, because that's what I got. So since it's a quotient map, it's already continuous. So this part is easy. And then we have to prove that if we map saturated open sets to open of X to open sets of Y. And let us take a set U, which is saturated and open in X. And then if we take a set, if we take the set P of U, P of U would be open in Y by definition. Since in a quotient map, if our pre-image is open, then its image would be open always. And then when we go the second way around, we have to prove that if we know that P is continuous and it maps saturated open sets of X to open sets of Y, then P is a quotient map. So how we go for that one? Firstly, we will do something to this definition. So we can say that this statement is equivalent to the statement that there exists a set B, which is a subset of Y, and for it we know that A equals the inverse image of B. So basically we say that P of A exists. Then when we know this, and if we have a set U belonging to Y, we have its inverse image, which is P inverse of, if we have it such that its inverse image is open, then sorry. Okay, so then we know that its inverse image using the statement. The inverse image of U would be open and saturated. And it would map to an open set by our condition stated above. And so we know that P of P inverse of U equals U, since whenever we, if we have a saturated set, it can be saturated only with respect to a surjective map. So our map is surjective, and from its surjectivity, it follows that P of the inverse of U equals U, and U is an open set. So basically we have proven that, so our condition gives us that since we are mapping saturated sets of X to open sets of Y, basically in order to have saturated sets, we have to have a surjective map. And then since P is continuous, we know that basically we know that for every open set, a set and Y is open if its inverse image is open on X. And then here we proved the other condition which we need, that if a set is open on X, then its image on Y is also open. And Thus, we have proven that P is a quotient map. And we know that these two statements are equivalent to our definition for a quotient map. Okay, so I will continue to the next slide. So there is one other statement. It's not equivalent to the definition of a quotient map, but it's close to the definition of a quotient map. So if P is a surjective continuous map that is open or closed, then P is a quotient map. However, there are quotient maps which are neither open nor closed, and we will have some of them in our examples. So let me remind you, an open map is, just give me a sec so I can find my notes. So an open map maps each open set U of X to an open set F of U in Y. And it's the same way for a closed map. It maps each closed set of U to each closed set U of X to a closed set F of U in Y. So I think this one is straightforward because it's a surjective continuous map, which means that we already know that it is a surjective map. We already know that the if and only if condition which we have in our definition works in one direction. That, I mean, if due to its continuity, if our image set is open, then its pre-image would be open. And since it's an open map, we know that if our pre-image set is open, then its image set would be open. And we get that P would be a quotient map. So here is our first example. So if X is a subspace 0, 1, we can with the closed interval from 2 to 3 R, and Y is the subspace of the closed interval from 0 to 2 of R, then the map with P defined that way is surjective, continuous, and closed. Thus, it is a quotient map. However, it is not an open map. So we say that it is surjective since each possible image from our Y is mapped to at least one member of our X. And then it is continuous since the pre-image of every open set here is an open set here. And we can see that closed sets from X will map to closed sets in Y. So we get that it's a quotient map. However, it is not an open map because this set, 0, the closed interval from 0 to 1, is an open set on X since by lemma 16. I needed to remind myself for this one. Probably you may remember it, but I will just mention the lemma. It's lemma 16.1 that when we have subspace topology, then a subspace which is a set from subspace which is equal to the intersection of an open interval on R with the subspace is an open set on the subspace, so we can show that 0, 1 equals to the interval from, let's say, minus the open interval from -1/5 to 1.5 and intersection with, so I forgot this, an intersection with x. So it is an open set on x. However, its image on y would be again the same set. The same set. It will be the closed set from 0 to 1, which is not an open set on this subspace. So we see that our map P is not an open map. And then, so if we change, if A is our subspace, which is the semi-closed interval from 0 to 1 in union with the closed interval from 2 to 3 of x, and we get the map Q, which maps A to Y by restricting P, it is continuous and surjective, but it is no longer a quotient map, since now we have the set 2 to 3, which is open in A, and it is also saturated with respect to Q. But its image, which is 1, the closed interval from 1 to 2, is not open on R. So it is not a quotient map. Okay, so we have our second example. So we remember that pi1 is the projection of the product topology of R to R, and pi1 is continuous and surjective, since every open set on R, its inverse image is an open set on R cross R, and it is also an open map. Okay, so here's my first point where I was not, okay, so I tried numerous ways to show myself that this set is closed in R cross R, but I was not successful in any. So maybe you can help me and remind me why C would be closed in R cross R. Zikang, do you want to help me with that?
I don't have a very good idea.
Maybe I can give you a very small hint.
Mm-hmm.
So to see it's close, we'll check it by definition. You can try to do that, and you can try to use the closed set on a metric space. It must satisfy some properties, and as long as it satisfies that property, then it's a closed set. Or you can also try to prove it by, well, prove some set is closed. You just need to prove the complement of this set is open, right?
Yeah. So as for the second approach, like graphically, I was thinking that basically the entire space, which is not the graph of xy equals 1, can be it can be the unions of many, the infinite union of many small rectangles. However, I don't know how to put it out with mathematically. I imagine it in my mind as many rectangles which are very, very small, and their union would be an open set.
So what would be the definition of an open set?
It's a set contained in the topology of R, and it would be a finite intersection of other open sets or an infinite union.
Yes, that could be a very that is one of the definition, and there is actually well, in R there is actually a more useful way to try to find whether a set is open or not, which is in Rn. I mean, if you have a set, you want to check whether it's open or not. You just need to see, okay, for every point on this set, whether you are able to find a small ball, which is an element of the subbasis, such that it contains this point and the inside of this set, right? I hope you still can remember this. An open set means for any point, you can find one element on the subbasis such that the subbasis contains this point and was inside of your set. Right? So you can imagine you have an open ball. So why this open ball is open? Well, you just can imagine for every point on this open ball, then you can always draw a very, very small, tiny ball, which is open. And it inside of this open ball and will not intersect with well, outside of this ball, and it contains that point. This is the intuition on our end about what is an open set. You may have a better idea after we try to do some exercise of this chapter. Okay. Now let's try to, you can try to use this property, well, which is the most usual way to check whether a set is open or not, to check why this complement of this curve is actually open. Okay, try to do that.
Um,
就是 Holly, do you guys have any idea about this?
I mean, for the basis element in the product topology in this R2, can we draw a ball or just the intersections of two rectangles? Like,
Yeah, I mean, in R2, it doesn't matter, right? We've learned that whether you choose the subbases as ball or as rectangles, it doesn't change, right? Both are okay. It doesn't matter.
yes, right. Mm-hmm. So for this one, I think I try to draw something on it maybe. Like if you want to show like this region is open for any point in it, we can always find like a circle. Contains in it, and it does not intersect with this line and this curve.
That's a very good start. That why you can always find this this circle. What if you cannot find? What happened?
So like there is some other points. Like it. So I mean that means some point it does not satisfy xy equals 1. Or how to form?
Can we use something in the way of okay, so the way it's in my head right now is if we have a line which goes like this, so the entire line is an open set on R cross R, I think. Is it an open set there?
Is it open in R cross R? Mm-hmm. Probably no, right? Because it's very very similar to this kind of curve, right?
Yeah, it's not open. Okay, so my thoughts were wrong.
But well, you can try to imagine what if you have a straight line, then how can you show, for instance, the straight line on R cross R is actually a closed set. I think Zikang's first step gives you a very good hint about, what if you have a straight line?
If I have a straight line, I can use the rectangles.
Mm-hmm.
I'm so sorry.
I think you are very close. Okay, maybe let's see. Okay, what happens for a straight line? Okay, if you have, for instance, a horizontal line, right? As Zikang said, how can you show that this horizontal line is actually a closed set on R cross R? As we mentioned, we just need to show that, okay, R cross R subtracts this horizontal line. It's actually an open set, right? Which means for every point on this complement of this straight line, you want to find some open disk, contain this point, and does not intersect with this straight line, right? So what kind of, for instance, I gave you this point, what kind of open disk you can find?
So it would be
The metric between.
Yes, that's right. Well, this might be too close. Maybe we can just take the half of the distance of this circle, right? Then you can see that this disk contains this point, and you will know that none of the point on this disk are on this line, right? Because otherwise this point, the distance between this point and this straight line is this one, but any point on this disk has smaller distance to this point, so which means none of them are on this line, right? So which means whatever point you give me, I can always draw this kind of small disk such that it's away from this line and it contains this point and it's actually an open set or it's actually a subbasis, whatever. Okay. So this is a way you try to find a small subbasis away from this open set for a straight line, right?
Right. Yes.
But then problem is, what if you do not have a straight line, right? What if you have this kind of curve, this hyperbola? Then the problem is we don't know whether there exists some distance between this point and this curve, right?
Mm-hmm.
Mm-hmm. So then, what happens if there does not exist, right? If there does not exist, such kind of ball if for any epsilon greater than 0, right? Let's say this point, I choose it to be A. And this set is C. B epsilon A, which means a ball or a disk centered at A with radius epsilon intersect with this C is always not equals to 0. Well, empty set, right? It will always intersect with this this curve, with this hyperbola, right?
Right.
So we try to argue by contradiction, right?
Mm-hmm.
Then that means, okay, there exists epsilon belongs to this one, right? There exists some point, it belongs to this small disk and the curve, right?
Right.
What does that mean? That means, well, it seems that this kind of x epsilon, or let's choose it to be discrete, like epsilon equals to 1 over n, that doesn't matter, okay? This sequence has a limit. By definition of limit point, right? By definition of limit point, A is a limit point of this sequence. Remember, what's the meaning of a limit point? Limit point means, okay, you try to find some kind of, well, this is a metric space, so it doesn't matter. We can use our definition on the analysis to define something like a limit, right? That means you have a sequence of points. It will approximate this point A.
Mm-hmm.
That clear?
Yes.
And is that possible? So you can see that all this point x 1 over n, they are point on R2. Let's use this kind of vector notation. They are point on R2. All this kind of point are all in this circle, or in this curve C, right?
Yes.
And A is a limit. That means, okay, if you take the original limit, which we learned from calculus class, right? As n goes to infinity of this kind of thing, it must equals to A. Right? This
Right.
limit is a limit we learned from calculus. So that means if you choose this component by component, let's say A equals to XA, YA. Okay? And x1 over n is equals to, let's say, xn, yn. Okay?
Mm-hmm.
We must have the limit as n goes to infinity, xn equals to xa, the limit of as n goes to infinity, yn equals to ya. That clear?
Yes.
So we know that xn times yn equals to 1. Because they are always on your curve, right? So we must have xa times ya equals to 1, which is a contradiction.
Yes.
We choose some point not on the curve, but eventually we show that this point is actually on the curve. So which means there must, this kind of assumption will not be true.
Oh, right. Yes.
Okay. So you can see that this kind of proof also works for any kind of continuous function forms a curve, right? If you have a curve that forms by a continuous function, then it's always a closed set.
Yes.
Okay. So this is a very very useful trick about how you can show or how you can find some set is a closed set or an open set. Just as a combination of topology and maybe I should clear everything.
I'm sorry.
Yeah.
I was trying to do something, but I'm so sorry. I took a screenshot and I wanted to send it in the group chat because I think it was very smart and nice and we could use it later. I'm sorry.
It's okay, yeah. But yeah, basically, I think you just need to get the idea. The idea of the proof is, I think, is manageable for you, right? I hope so. Well,
yeah.
Because the proof is basically like a calculus proof, a calculus type proof. So you can try to think about it. Okay.
So this would be the way to prove for any curve.
This is actually you actually can prove for any curve generated by a continuous function. But if you have something not continuous, then you may need to discuss about it, because then the limit point on this curve may converge to some other point that are not on this curve, which may be quite weird, but it happens in some situation.
Okay. Thank you.
Yeah, it's not a short proof, but it is something that will kind of your proof. Well, later when you do the exercise, you will see that.
Okay, so now that we know why C is closed on R cross R, we go to back to our example, and pi 1 of C would be R minus 0, since basically this point, no point which lies in X or Y would be on this graph. So R minus 0 is our pi 1 of C, and it is not closed because 0 itself is not an open set on R. And however, if A is the subspace of R cross R, which is C with union 0, then the map which maps A to R, obtained by restricting pi 1, is continuous and surjective, but it is not a quotient map, since 0 would be open on A and saturated with respect to Q. However, its image would not be open on R. So I think its image would be 0 again, and it's not open on R. So basically, Q is not a quotient map. Okay, so next is a definition, which is for the quotient topology. So if X is a space and A is a set and P maps X into A as a surjective map, then there exists exactly one topology T on A, relative to which P is the quotient map, and T is the quotient topology induced by P. So T T is the topology consisting of those subsets U of A such that the inverse image of U is open on X. And, oh, wait, this is for the next part. So maybe it's 3 of us. So maybe we have 3 properties which we have to show in order to show that T is a topology. Our first property is that the empty set and the entire set, which our topologies that are open sets. Then our second property is that the unions of the infinite unions of all infinite unions of open sets would give us an open set, and finite intersections of closed sets would give it open sets would give us open sets. So maybe Holly, do you want to show us that the empty set and the entire set A are included in T and are open? Hey, Holly, are you here? Can you hear me? Oh, so can you show us that the empty set and the set A are included in our topology T, our open sets in T? Okay. Zika, maybe you want to help?
So we need to show that this P inverse of U is open on X, or
We need to show that T is a topology. T
I see.
is a topology. So we have 3 conditions for
Yes, to check. So first is it contains the empty and the whole set.
Yeah.
So the empty set is just the inverse of the empty set, and so the X must contains the empty set, so it is open. Sorry. What?
And it's the same way for A, since the inverse image of A would be X, since it's surjective. And oh, I think I wrote something stupid here, which I don't need to write. And X and X is open on X, so this would be open on X, and then A would be open on Y, on A, sorry. And our next two conditions are for infinite union, for unions and for finite intersections of open sets. So I'll just turn to the next page where I have all three conditions printed out, since it will be quite a struggle for me to write with my computer the other two conditions. So this is the first one. And then the inverse image of a union of open sets would equal to a union of the inverse image of open sets. Thus, we see that the union of open sets would also be an open set, and it goes the same way for intersections. I will leave it just for a little bit. And so you can, yeah, okay. So our next example is we have P, which is the map of the real line R onto the 3 points at A, B, C, defined in this way. So P of X equals A if X is greater than 0, B if X is more than 0, and C if X is equal to 0. So it's, do you think you can use our definition for T given here on this slide to draw the topology, the quotient topology of example 3? So what we need is that basically every inverse image of an set would be open. Wait. just have the picture with me, and I will, okay. I'll go back here. So we need to have subsets U of A such that the inverse image of U would be open on X, and basically we would have open sets in T when their inverse image is open on X. So if we have the points A and B and C, the inverse image of A is an open set. So it would be an open set. The inverse image of B is an open set, so it would be an open set too. And then their union will be also an open set. And then the entire set will be an open set. And that's how we get our quotient topology for the set A defined by P of X. And from then on, we have another definition for the quotient space. So
by the way, so just a very quick comments. So you can see that this kind of idea about how you can, first you have your definition of, I gave you a topology, you can say whether a map is a quotient map or not. And then this kind of definition just say that, okay, as long as you give me a map, I can find the corresponding topology such that this map is a quotient map. And then the very good thing is this topology is actually unique, right? So for this topology, it's actually the, well, you can try to imagine it's actually the least or the optimal topology such that you can get the map to be a quotient map, okay? And this is a very interesting and important idea in math. So of course, I gave you some map. You can find infinite many topologies such that this map becomes, well, a lot of topology at least, such that this map becomes a quotient map. But then how can you find one instead of a lot? In just, well, just because we try to find, because we want to find some kind of one-to-one correspondence, one map corresponding to one topology. And then here is the idea how you can find one, a unique one, okay? The uniqueness is very important, and you can get the uniqueness by saying some kind of optimal, okay? Well, in math, it's always like this, and at this moment, maybe you cannot really get this point, but in the future, maybe you can see more examples about it, okay?
thank you. Okay, so I will move on to our next definition. It's for the quotient space. So if X is our topological space and X asterisk is a partition of X into disjoint subsets whose union is X, then the map P, which maps X into X asterisk, is the surjective map that carries each point of X to the element X asterisk containing it. And the quotient topology induced by P, it should be a lowercase p, I'm sorry that it's uppercase. The space X asterisk is the quotient space of X. So we can remember that so basically whenever we do, I just need to remember the words. Whenever we have an equivalence class, we have a corresponding partition of a set. So if we have whenever we have an equivalence relation on X, we have a corresponding partition on X, and we have basically our X asterisk is basically the space which contains all of our equivalence classes. And that is why we would also call X asterisk the identification space or the decomposition space of X. And a subset U of X asterisks would be a collection of equivalence classes, while their inverse image would be the union of those classes. So an open set of X asterisk would be a collection of equivalence classes whose union is an open set of X. And there are two examples related to this definition. So there are example 4 and example 5. However, I will start with example 5 because I found it a bit more intuitive, and I had some unclarities on example 4. And then maybe after we finish example 5, we can discuss example 4 together. So if we have X as the rectangle of the closed interval from 0 to 1 cross the closed interval from 0 to 1, it's this rectangle. And if we define the partition X asterisk of X to contain all one set points, X cross Y, where X and Y lie in the rectangle, so it's this type of points, and all 2-point sets such that X cross 0 and X cross 1, where X belongs from 0 to 1, is basically this type of set. And then for Y, it's this type of set. And the 4-point set of the 4 corners of the rectangle. Then our definition for X asterisk helps us build a torus out of a rectangle. So basically we can see, so these things should be shaded, and they're not shaded in my book. Actually, in the paper, in the hard copy of the book, they're not shaded at all. So I was a little bit confused at first because I have the hard copy at home and I'm using the hard copy, not the online one. And after I Googled and I was looking for this diagram because I didn't want to draw it myself. And I thought it's really good. And I saw it on the internet and I was like, oh wait, these are the shaded regions actually. And it makes a lot more sense with them. So our shaded regions are our typical saturated open sets in X, or they're collections of open sets in X asterisk. And so what we see that is okay, so the image of each of these sets and their piece and open set of X asterisk. And here we see their images. So this is the set U, and it would come in the inner part of the torus. And set V would come on the inner edge, and set W would be just somewhere on the torus. So I guess that probably this is, like, I guess it's easy for you, but if it's not, as it was not for me, the way I actually figured it out in my head was I used a sheet of paper. So if you join the ends of the sheet of the paper and make a cylinder, you basically make all the Y points, you map them into, so you would map each of those sets which are of 2 points, you would map them to 1 point. And then if you curve the cylinder in order to get your torus, you would do the same thing for all those 2-point sets. You would map them into 1 point, and you would map the 4 corners into 1 point, which comes right here. And So that's for example 5. So basically this is the, our partitioning into X asterisk is the mathematical way to
by the way, so actually, there actually in our textbook there is a better picture about this example. You can see that at the very beginning of this section, how you can make a torus. Okay, in the 22.1, that is how you can make the torus by doing this kind of well, cut and paste, or maybe there is no cut, there is no cut, but there's just a paste. Okay.
Okay, and our next example is example. Okay, here's the example 4. So it's basically about building a sphere out of a unit ball. And I hope that we could discuss this together because so it's quite intuitive to look at, but I wasn't able to prove this part. I wasn't able to prove the homeomorphic part. So I'll first read it. So if X is a closed unit ball where X cross Y such that X squared plus Y squared is less or equal to 1 in R squared, so this is our X, and X asterisk is a partition of X which consists of all 1-point sets X cross Y for which X squared plus Y squared is less than 1, along with the set S1 which is X plus Y such that X squared plus Y squared equals to 1. We can show that X asterisk is homeomorphic with our unit 2 sphere, which is defined by S2 equals XYZ, such that X squared plus Y squared plus Z squared equals 1. So it's what I got so far, what my direction of thought was that basically if we map S1, it's all points for which X squared plus Y squared equals 1. And there is a way in which we can use our X asterisk to build half a sphere by mapping each of these points with the function f of X, Y equals square root of 1 minus X squared minus Y squared. And pretty much if we, in order to build the whole sphere, we need F and F1, which equals the same thing, however, with the minus in front of the square root. And that's basically how far I got. And I don't know how to prove this homeomorphism. So in order to prove the homeomorphism, so firstly, please correct me if I'm wrong. So what I got is that X asterisk is homeomorphic with this subspace if there exists a homeomorphism between them. And in order to prove that homeomorphism, then we have to prove that there exists a function which is continuous, I think, and I'll check the exact wording, but basically we have to prove that there exists a continuous function which maps X asterisk to R3, and then its inverse function is also continuous. So can you help me to show the homomorphism?
Or just a remark about the construction. So don't forget, when you try to build the map, right? It has to be a map from R2 to R3, right? So your map should contain 3 components. Don't forget this if you really want to build that.
I'm sorry, I just don't quite understand. What do you mean by 3 components?
Well, I mean, you can see that this function, if you try to build a function or a map from R2, from this disk unit ball on R2 to S3 unit 2 sphere, which is on R3, right? Let me write it here. So you want to find a map P from this ball. Well, does it have a name? Yeah, it's named X, right? Maps X to this X star, right? Or, okay, let's call it X star here. Okay. Then what do you want? What do you want X star to be, right? You want X star to be something more or less like S2, right? So which means you want X star, or you want to find a map from a subset of R2 to a subset which is homomorphic to the S2, which is a subset of R3. Yes, we may try to do that. So which means you must have this 3 component on your map, right? Otherwise, it doesn't really, it will not be some subset of R3. This is my point. Is that clear?
Yeah. So if we use X star, which is defined here, how do we get that? How do we get our 3rd component?
This is actually not so easy, I think, but intuitively, I think it's actually very similar to the torus one. Okay, I hope intuitively you can imagine what happens in this graph. So for the torus, you can see that you actually got a letter, well, a letter paper, letter size paper, A4 paper, and then you try to fold it to make it a cylinder, and then you try to fold it again and make a torus, right? Here, what you are doing, what you're trying to do is you try to, maybe I can, I don't know whether it's you can see this or not. For instance, you still get a piece of paper. This is very hard for you to see. You still get a piece of paper, and then you take, well, this ball and this paper are basically the same thing. Then you take one middle point of this paper, okay? And you try to pass all the boundary of these papers and try to make it somehow like a ball, right? Somehow like a sphere. So this is an intuition, right? You still try to do some paste, and then intuitively you can see that from here to here. And what is the equivalent class? The equivalent class is you try to pass all the boundary to one point here on the north pole, right, of this sphere. And all the rest, it doesn't matter, right? All the rest is just well, everywhere. Okay, it's just on this on the surface of this sphere. Or on the other side, you can just imagine how you can get a flat plane from a sphere. How you can get a flat plane from a sphere? Well, that's also not so hard, right? If you have, let me see where can I find one. Let's assume this is a, well, this is a sphere, okay. It's a 3D shape. How can you get, how can you flatten it? Well, what you can do is you do a cut on the north pole, right, of the sphere. And then you try to flip it, you try to flatten it. And then try to push it like a piece of paper, try to stretch it. And then you will see that if you try to, as long as you have a hole on the north pole, you are able to try to make it a plane, right? Yeah, so this is the idea. But of course, if you try to write down the explicit map, that's another story. I would guess maybe the map you wrote should be correct, somehow correct. It should be something similar, I think. Maybe something like 1 minus x squared minus y squared, comma x, comma y, this kind of thing. You can see that x squared plus y squared plus z squared, the three components square of the sum of the square of three component equals to 1, right? And yeah, and when x squared plus y squared equals to 1, then this part equals to 0. The one of the component equals to 0. So is that okay? I guess something like this should be fine. Maybe this is not in details. This may not be correct, but I believe something like this should be correct.
I was just thinking the same thing, because this morning I thought that this would be the way, and then I figured out that this would give us actually half of the sphere minus some of the points where it would repeat itself, and that's why I was.
Yeah, that's right. So which well, is that right? Let me see. So let's see. So what may be on the sphere but not on this curve? Oh yeah. So you're right. I think you're right. So you just need to have some kind of plus or minus sign right in front of the first component. Yeah. Yeah, I think you just need to have some plus or minus sign because for this one, you will have the first component will always be plus, right? So you just want what you may want. Let's see.
I think it would give us basically only this half if we have like this. We would have only the part which is on the positive z. We don't have the part on the back.
That's right. That's right. So what would be the boundary of this thing? It will not have this well, minus part, but in that case, well, when x squared plus y squared equals to when x equals to 1, we need something like a minus 1 in we may need something like
And we also have this point and this point. This point, which were defined by this definition, they should be the same as the top point.
So what is a North Pole? The North Pole or this PU somewhere like this should be when I think when x squared plus y squared equals to 1. Wait. I think this point, which is a North Pole, yeah, North Pole should be like z equals to 1, right? 0, 0, 1. By the way, maybe we should rewrite it. Maybe we should rewrite it like to make it. It should be x, y square root of 1 minus x squared minus y squared. This could be the map, right? And then at this point, you will get x equals to y equals to 0, right? So then this point is North Pole, and for the South Pole, this is not correct, because then on the South Pole, what you do want is this becomes a minus 1, right? So maybe you really want something different, like how do you play with this function?
I think it will work that way, but we need just if we change the axis, basically if we say that our North Pole is here and our z-axis, it's not, or if we if that's not our y-axis, but it's our z-axis, and then if we add our minus condition, we would have the other half of the sphere, and then we would have the South Pole, which would be -1.
But then you don't really have a map, right? Because for any single x, y, you should have a 1 point. Right?
Yeah, that's the other problem with it. Yeah.
Mm-hmm. So again, I think we should try to say that we should first try to fix the North Pole and the South Pole, right? So which means when you
I just came up one idea. I don't know whether it's correct. How about just change the coordinates, like to can I write here? Like make this point is like 0 and this one is 1. Draw so this one is 1, maybe this is the 0 point.
Yeah, that sounds pretty reasonable.
So this works for the North Pole and the South Pole, but I don't know whether works for other points.
I think yes. I think the idea should be correct. You can see that on the boundary of your original disk, or the original disk, you have on the boundary, it must map to the north pole, right? So which means when you have x squared plus y squared equals to 1, then you should have a single point as your image, which is maybe this point, whatever. Then I think what we do here is we have x squared plus y squared equals to 1, but then we may have we have a lot of points, right? So this map we construct may not be accurate. Remember, what we want is, well, for any point x squared plus y squared equals to 1, we must have a single image. What kind of a map we can get? It is actually a single image. So what we want is so how about this? So basically we want this is like well, this should be looks like this kind of radius. This kind of radius should be mapped to this kind of half circle, right, on the ball. Then in this case, what you want is, for instance, this this diameter should be mapped to the big circle on the sphere, right? So maybe we can try to write it as a polar coordinate. Is that an easier way? Maybe that will be an easier way. Say, you can see that the point here corresponding to, but that would be a little bit complicated, but I think it's okay. You can try to map it like, well, how to simplify it. So you can try to map it first. You try to draw the polar coordinate here, and then for every point on this well, the polar coordinate on this R2 will be rho theta. Okay, and then for each theta, it will corresponding to here, any point here should be any point on this well, 2 sphere would be 1 let's say, well, let's use another notation, theta tilde phi tilde. Okay, this is still the polar coordinate. And then if you want, this is for any single point on this 2 sphere, right? It can be determined by 2 angles. And the corresponding theta here should map to, I think the corresponding theta here should map to the corresponding theta tilde here. And the corresponding rho here should be mapped to, because for the same rho, you will get this this kind of, well, what's the name of that? This kind of circle, right? For the same row. So the row will determine, somehow row will determine phi tilde, right? Do you get what I try to explain?
Yes,
So-
I think
Mhm.
like this coordinate is very like the sphere coordinate. I don't
Yeah,
right.
spherical
So
coordinate, or it's, well, you can also call it polar coordinate, but yeah, that's right. So for
So-
any point on this, yeah.
so this phi tilde is like, you mean this radius is like this semicircle, and so this phi tilde may be just some.
Yeah, you can see, okay, if we have a 3D coordinate, then any point on this 3D coordinate can be determined by 3 coordinates. One is the distance from here to the origin, right? Another one is the angle between this line and I think XY plane. I forgot which one is theta tilde, which one is phi tilde, but it doesn't matter. Let's say this one is phi tilde. This is the temporary well, notation. It is not official. And another coordinate that can determine this is phi tilde, which is the angle between this vector and the XY plane. Okay, and also another angle theta is the angle between this vector, let's say this vector, and XZ plane. Okay, we call it say theta tilde. Okay.
Right.
Oh, it's not XZ plane. I think it's actually Z axis. I'm sorry. Z axis. I think. Oops. This is X, and you have a vector X. This vector can be determined by the angle between this vector X and the XY plane, and the angle between this X and the Z axis, I think. This is theta. Well, my drawing is very poor, but I think you can try to imagine what happens. And then you can see that if you map this theta to the theta tilde, then for the same theta, am I right? And let me see. For the same theta, you should have, well, you should have, if you have a point on the same theta, you should have a big, it must be on the big circle. It must be on the big circle. Yes, I think I'm, do I mess it up? Maybe I mess it up. Well, sorry about that. It seems I make it over too complicated. But well, this problem, I think it's over too complicated, and it's actually very technical. So I don't think we should get stuck on this one. But I think the basic idea is, if you have some point here, right? You want to map it to this sphere. Then how can you map it? Well, you can try to think, okay, you try to map this point, the center of this disk, to the North Pole, or Well, that makes the problem easier, okay? To the north pole, or to the south pole of the two sphere, and the boundary to the north pole of the sphere, okay? Then what happens is, then for each of the diameter of this disk, it maps on the sphere, it maps to the big circle, okay? So which means if you have the same angle, the same theta, you will be on the same big circle, okay? So you try to bend this straight line, the diameter, to a circle. And then if you are in the same radius, for instance, if you are in this same radius, like this, what happens? What this kind of smaller circle on the disk will maps to this kind of circle, right? That should be what happens. Okay. So if you try to imagine it like this, then I believe you will be able to try to find the maps something like rho theta to the spherical coordinate or the polar coordinate on R3. But I also forget what is the correct way to write this kind of thing in geometry. And since you may not learn this kind of geometric course, so maybe let's skip it. Okay, this is I think this is too complicated and too technical. I don't think it's necessary to know. You just need to get the idea. And in our textbook, you can see that we don't really have the explicit map. For example, 4 and 5, right? So you just need to get the idea about how you can build the quotient space. What's the idea about the quotient space? The quotient space is just you try to pass to something, okay? So now you try to play with it. Now it's really taste like what you can imagine about the topology, I hope, okay? But by the way, another comment on this is maybe Zikang, I hope Zikang will have a better idea about what's the meaning of this quotient space. Because this is really like the quotient group we discussed on the abstract algebra. Okay.
Okay. Quotient group.
Yeah, it's not very easy.
It's hard.
But you can see that it's actually a common idea, and it's actually a very important idea. So in topology, how you can do this play with some kind of donut and cup, like we mentioned on the WeChat group, right? How you can play with that? You can play with that by, you can do the cut and paste by doing this kind of quotient space, okay?
Okay.
Yeah, at this moment, I think you don't need to worry about the details, and we may try to write down something more when we try to do some exercise. At this moment, let's try to be kind of brutal, okay, at this moment.
Okay. Thank you for the discussion. I suggest that we stop here and we continue tomorrow with the rest of the chapter, since it's almost 4 p.m. here, and it must be something like 9 p.m. in China.
Yeah, that's totally fine. And again, last remark. So in this section, as I mentioned, it's complicated, I agree, and it's not very easy to imagine. But in this chapter, you can really taste, this is actually the taste of topology, how you can think in the way of topology and rigorously, okay? You don't really just play with the donut, right? Play with the donut, everybody can do that. But how to describe it mathematically is not that easy. You can see that. But this is really what mathematicians do.
Thank you for the discussion and the help today.
Well, okay. Thank you very much for the presentation. Yeah, and you guys can try to think about this kind of problems, and I hope you can try to do some exercise in the future. Okay, and maybe we can discuss it this week or next week about some exercise after on these chapters. And